Hey everyone, let's solve this challenging system of equations. We are given here a squared plus b squared equals 61, a cubed minus b cubed equals 91. Both a and b are elements of the set of real numbers. Find the values of a and b. You can pause the video and see if you can solve this challenging system of equations. Now let's solve this problem together. Let's begin by visualizing the graphs of these two equations. This blue circle is the graph of a squared plus b squared equals 61, while this orange curve is the graph of a cubed minus b cubed equals 91. To solve these two equations simultaneously means we are looking for the coordinates of the points of intersections. And in this case, in the set of real numbers, there are 2 points of intersections here, this part here, and this other part here. In the first point of intersection, there is a value for both a and b. In the second point, there is also another value for a and b. So that is what we are expecting to find as we solve this system of equations. So let's now proceed to the algebraic solution of this problem. Let's begin by calling the first equation as equation 1 and the second one as equation 2. Let's start with equation number 2. Notice that the left side of this equation is a difference of 2 cubes. So let's recall the formula for difference of 2 cubes. Its factored form is this right side here. So using now this formula, we can now write a cubed minus b cubed in its factored form this way, following this formula, and we just copy the right side. Notice that we have here a squared, which is similar to the first term of equation 1, and b squared, which is similar to the second term of equation number 1, but equation number 1 does not have the middle term ab. So what we can do is, let's set this aside, and we are going to use this later on. Let's deal with equation number 1 first. We want to have this middle term ab in equation number 1. So let's add ab to both sides of this equation, and this is the result. The left side is exactly this part here, and therefore we can now replace this part by 61 plus ab by substitution. And let's do that. So we now replace the second factor by 61 plus ab. All the rest are just copied, and this is now the equation that we are going to work with. Next, let's define new variables. Let r be equal to a minus b, and let s be equal to the product a times b. This means that this a minus b can be replaced by r, this a times b can be replaced by s, and we have a more simple equation to work with. Let's call this equation number 3, and let's set that aside, and let's deal with another equation. Let's go back to equation number 1. Our goal is to express this also in terms of variable r and s. As this is written, there's nothing much that we can do, but we can change its form without changing its value and come up with the expression a minus b. This is how we are going to do that. If we subtract 2ab and add 2ab, basically minus 2ab plus 2ab is 0, we are not changing its value. But the effect of that is this part is a perfect square trinomial, and its factored form is the quantity a minus b squared, and we just copy all the rest. So you now have here the expression a minus b and the expression a times b, which we know have corresponding variable substitutions in terms of r and s, and we do the substitution now. Replace a minus b with r, replace a times b with s, and let's call this as our equation number 4. We now have here two equations in two variables r and s, equivalent to the first two equations, where the fourth equation is equivalent to the first equation, the third equation is equivalent to the second equation. So let's interchange equations 4 and 3, and let's deal with equation number 3. Solve this for s. Divide both sides by r and subtract 61 from both sides. We now have an expression in terms of s that we can use to substitute to this s here. So with s as 91 over r minus 61, then this equation now becomes r squared plus 2 times, instead of s, we replace it with 91 over r minus 61, and we just copy all the rest. And let's simplify this equation. Multiply each of the terms by r to eliminate the denominator r, and we simplify. R times r squared equals r cubed. This r and this r will cancel out, so 2 times 91 is 182. Then 2r times negative 61 is negative 122r. Copy the right side. Then we collect like terms. We subtract 61r from both sides, so negative 122r minus 61r is negative 183r, and we just copy all the rest. We need to factor out the left side of this equation. This is a cubic equation. By inspection, notice that if we let r be equal to 1, r cubed is 1. Negative 183 times r is still negative 183, but 1 minus 183 is negative 182 plus 182 equals 0. That means 1 is one of the roots of this equation. So the factored form of this would look like r minus 1 times another factor here that is equal to 0. But what is this other factor? Well, we can use synthetic division. So using synthetic division, we notice that there is no squared term, so we inserted 0r squared, and then we get all their coefficients in descending order. We already established that 1 is one of the roots, so performing now the synthetic division, we bring down this 1, and 1 times 1 is equal to 1. Put the result here. 0 plus 1 is equal to 1. Then repeat the process. 1 times 1 is equal to 1. Negative 183 times 1 is negative 182. Negative 182 times 1 is negative 182. 182 minus 182 is equal to 0. This means that this 1, 1, and negative 182 are the coefficients of the resulting depressed polynomial, which in this case is quadratic. So we now have 1r squared plus 1r minus 182. Then this r minus 1 is based on the fact that 1 is one of the roots of this cubic polynomial. So we now have this factored form, and this quadratic equation can also be easily factored. The factored form of r squared plus r minus 182 is r minus 13 times the quantity r plus 14. That is because 14 times 13 is 182, but 14 minus 13 is positive 1, which is the coefficient of r. So we have three factors, each equated to 0. r minus 1 equals 0. That means r equals 1. r minus 13 equals 0. That means r is equal to positive 13. r plus 14 equals 0. So that means r is equal to negative 14. But what is the value of s here? We know that s is equal to 91 over r minus 61. So that can easily be computed. Solving now for s when r is equal to 1. So this 1 is our denominator r here. This is equal to 30. Here, s is equal to 91 over r, where r is equal to 13, minus 61. This is simplified to negative 54. And here, s is equal to 91 over r, where r is negative 14. Then copy minus 61. This is simplified to negative 135 over 2. So we have the value of r, we have the value of s for each of these three combinations. So the ordered pair Rs therefore are 130, 13, negative 54, and negative 14, negative 135 over 2. These are the values of R and S. But what we want to find are the values of A and B. But we already know what's the expression for R in terms of A and B. The same with S in terms of A and B. All we have to do is do the substitution. So we know that R here is equal to 1, S is equal to 30. We copy all the rest. Based on this equation, we can solve this for A. A is equal to B plus 1. And substituting this B plus 1 for A here, that becomes 30 equals, instead of A, we have B plus 1, and we copy B. Distributing the b to get quadratic equation, b squared plus b equals 30. Write this in standard quadratic form. This is factorable as b plus 6 and b minus 5. That means b equals negative 6 and b equals negative 5. So we have two values for b, and we can compute two values for a also because a is equal to b plus 1. So solving now for a is equal to, in place of b, we use negative 6, copy plus 1. That gives us a equals negative 5. And here, b equals 5, so we have a equals 5 plus 1, or a equals positive 6. So the ordered pairs AB for this case is a equals negative 5 and b equals negative 6, and a equals 6 and b equals 5. This is now one pair of solutions for our original problem. So let's set this aside. This is now one of the solutions. Now let's go to case number 2, and let's also solve for the values of a and b using r equals 13 and s equals negative 54. So, going back again to our expression for r and s, then replace r with 13, replace s with negative 54. Here is the result. Solve this equation for a. That means we add b to both sides to get a equals b plus 13. And since a is equal to b plus 13, we replace this a with b plus 13, distribute b to the binomial b plus 13, and write this in the standard quadratic equation. But before solving this, let's check its discriminant. The discriminant is b squared minus 4ac, and check if the root is real or not. So solving now for the discriminant, we arrive at a discriminant that is negative 47, which means that this will not give us a real solution. The root here is imaginary. And we want only the real solution to this problem, so let's discard this case. Let's proceed to case number 3 and solve for a and b given that r is negative 14 and s is negative 135 over 2. Use the same procedure and check for its discriminant. The discriminant is equal to negative 296, following the same procedure as we did in the previous one, which means that in this case, again, the root is imaginary, and we are only after the real solution to the given equation, and therefore we discard it. So the only real roots that we arrive at are the ordered pairs AB, negative 5, negative 6, and 6, 5. To check if these solutions are really correct, we substitute the values to the original equation. If we replace now the first equation with a equals negative 5 and b equals negative 6, here is the result, and we arrive at a correct equation. Replace the second equation with the same ordered pair a equals negative 5 and b equals negative 6, and again, we arrive at a correct equation. That means our first pair of solution here is correct. Now check for the second pair. Do the same procedure, replace a and b with the ordered pair 6 and 5, and we arrive again at a correct solution. Replace the second equation with the same ordered pair 6, 5, and we arrive again at a correct equation, which means that the second pair is also a verified root of the given original system of equations. So this verified that our answer is really correct. These are the two pairs of real roots for this system of equations. All the other roots are non-real roots. This is indeed a challenging algebra problem.